So, now solution number 4. Solution number 4 is put one white marble in one of the bowls. Doesn't matter which bowl. I keep putting it in bowl number 1.
It doesn't matter which bowl, I would think. It's
On the wall. Because why? Right, he's randomly selecting a bowl. Remember that the line was he's going to move the bowls around once you're blindfolded, so you don't know which bowl is which. So since it's random, there is still a 1/2. There's a 50% probability of which bowl you grab every time. It doesn't matter if it's the left bowl or the right bowl, as long as it's in one of those 2 bowls. Is that fair? Is that believable? You guys okay with that? Okay, good. So solution number 4 is bowl number 1, 1 white marble. Bowl number 2, the rest. Now, we can follow the logic we followed over there mathematically to figure this out and see how the numbers hopefully agree with what we're seeing up here. We've got about 74%. We picked up about a 1.5 percentage wise over here. Let's see if we can make our math match that as well. Okay? So, we still, from bowl number 1, are going to live 100% of the time, half the time. Is that fair to say? We're going to live 100% of the time, half the time. Why the 100% of the time? Because there's one white marble in the bowl. So if you grab it, this is the key word from Ryan's statement, if you grab the bowl. So 100% of the time, why half the time? Because there's 2 bowls and you have to get that bowl to live 100%. So taking all that into account, that represents 50% of the livability of this solution. So 1/2 of the 100% becomes 50%. So once again, we've already done better than solution 1 and 2 with that bowl alone. With that bowl alone. Fair enough? You guys buying that? Good? Fair? Good. All right. Bowl number 2 is where things change a little bit, yes? The same logic applies. If you get that bowl, there's still a chance of living. But what is the chance of living now in bowl number 2? It's half of, well, now it's 9/19, isn't it? It's 9/19. Say that again. Well, thank you. I was going to ask you to do the math for me because I can't do it in my head. That ends up being about 47 and some change % of the time, which is a little better than our 44.5% of the time from the previous one. So you're going to end up with half of that 47%, which is going to be roughly, what is that, 23?
23 point, I'd say 24.
Sure, we'll call it 24%. Make you guys happy? That's fine. I can live with that. So it was 22.25%. It's gone up in that bowl a little bit more to 24%, which means overall, we've got about a 74% chance of living, which agrees pretty nicely with what we're actually seeing happening in Excel bouncing around. Pretty cool, huh? Pretty cool. So what I'll do for next week is I'm going to have a quiz built for you guys so you can explore this too with a different situation, a different scenario. I might change the number of marbles or I might ask a different question or something like that. But this is the kind of question I want to train you guys to think about leading into a statistics probability-based course. It's not an algebra question. There's a little bit of arithmetic in there, of course. We had to do like multiplication and stuff like that and averaging and whatnot. But the idea is it's not just simply solve for x, although that's important. I'm not saying it's not important. It's just not the end result. The end result is being able to analyze this question. Why is this question so tricky originally? Why is it so tricky originally? Oh, good. Good. There's 2 different ones. The number of white in the first and the number of black in the first. Because once you define those, the other ones are guaranteed. Tell me your name again, too. Taryn, thank you. Good. So we have got 2 things our mind has to keep track of. Very good. Why else is it tricky? It's not standard. I know that for a fact. It's not the kind of question you had in Math 60. Kind of unfortunate, actually. You shouldn't have done stuff like this in Math 60, in my opinion.
Well,
go ahead, Tammy, go ahead.
If you look at it, you're thinking you want a 50%.
Ah!
That's
Right!
what you're originally thinking.
How many of you, thank you for that, didn't mean to scream like that. How many of you immediately said, well, you can't do better than 50-50? Was it how many of that was it with your first gut instinct? Exactly. Exactly. The first gut instinct is that it's 50-50. I mean, you got half black and half white marbles. Done. There's no way you can manipulate that to make it any better than 50-50. until you stop and then think about it a little bit. And you start analyzing and trying different situations. Kind of cool, huh? Kind of cool. It's a neat probability-based math problem. Look at this. Beautiful 74% just hanging out right there. What's cool about this is you can then reset it and then grab other situations. You know, put 4. Like Tammy, yesterday you said, we'll put 3 or 4 white ones in the first and the rest in the other. That would still be better than 50-50, wouldn't it? Because you still have this situation right here. But this won't be as powerful as this is. You've got the most maximal chance of living. Isn't that kind of cool? With half black and half white, you still live, I guess, winning 3/4 of the time. Now, of course, there's 2 ways to look at that. You live 3/4 of the time, but then the other side of the coin is you either live or you die. You don't get like multiple tries at this. So, exactly, right? Exactly. So why do this? Why do this?
Aren't you gonna die anyways?
Well, no, he's gonna let you go if you pull a white marble.
Yeah, but if you didn't get that chance, he'd probably kill you.
Well, maybe. It's a little morbid. Dying in prison. Okay, forget the prison and forget the emperor for a second. Why would you... Let's just change the question that if you pull the white marble, you get to go home to your family you haven't seen in 10 years. So why bother doing this analysis? This analysis right here that we just did on the board required mathematics, and this one right here required 12,000 trials. You don't get 12,000, you get 1. So what's the point of doing all this?
To make it so that you don't have to test it on people.
Right, to make the same reason they have flight simulators for pilots. There's a couple ways you can learn to be a pilot. Give a wannabe pilot a brand new plane, put it up in the air and see what happens. Here you go, buddy, here's the keys, fill it up, wash the windows, have a good time. Oh, damn. That's expensive, that's dangerous, that's terrible. What you do is you put him in a flight simulator, put her in a flight simulator, and you replicate that thousands and thousands of hours worth of time. Then, when the time comes to turn that plane on or the helicopter on the first time and see what happens, you've got all this data backing up your decisions. This is a data-backed decision. If you were put in that situation where this was your decision, you would know the best way to load the buckets to maximize your chance of success. Does that make sense? It's what financial analysts do all the time. Where should your money go? Based on this and based on this and based on this, this is the best turnout. You only get 1 shot, so you pick the best turnout. Could it still fail? Of course, you could still die. What is it, 26% of the time, yeah? But you're roughly three times more likely to live. That makes it the best course of action. Is that fair? Guess by that logic? Good. Please, Ryan, go.
One thing that really affects you mathematically is something from the movie The Bridge Over the River Kwai.
Which I've never seen. Go ahead.
It's pretty much World War II people parachuting.
Okay.
But they said that they weren't training paratroopers at the time because of, I think, almost this exact mathematical issue, is that the training didn't help whatsoever because they have a, 74% chance of living once jumping out of the plane.
Okay.
So there was no point in even training these paratroopers.
That's given. You can't beat that.
Yeah.
I like that. So why fight the odds you can't fight?
Yeah, exactly.
You bring up an interesting point
So
that...
I'm saving time and money by not training.
Yes. And if more people made decisions based on data just like that, you would have you'd have more time and resources to spend elsewhere on things that actually could be. You're speaking in a lot of times of how actuaries actually set insurance rates for policies, and in a maybe a more realistic example for you guys, how Vegas sets the payouts on their gambling games. For example, craps. Anybody ever played craps? Right? Craps or roulette wheel. Spun a roulette wheel. I love these examples from a. Oh, good. And we're gonna look at it in this class when we get to that time when it makes more sense to talk about it. There are payouts for all those things. Like a craps bet. If you roll and you're betting a pass line bet, which means if you roll 7 or 11, you win. If you roll 2, 3, 12, you lose. If you roll anything else, you then have to roll that again before rolling a 7 again, or you crap out, or you line out, or whatever the term is. The chance of all that added up, if you do a similar analysis like we did right here, ends up being around 49.2% chance of winning. Vegas knows that. They know that, and they pay just enough to keep you losing a tiny amount each time. Because you can't fight the 49.2%. The movie Casino, which some of you may have seen, there's a classic scene, which I'm going to paraphrase and probably get wrong. There's a Japanese businessman that's visiting De Niro's casino. Correct me if I'm egregiously wrong on this story. And he cleans up. He goes in, I think he's playing poker. I forget which game it is, but he cleans up. He's killing it. And he stops. He grabs his chips, and he goes for the door. He's going to cash the chips in, take the money, and leave. And De Niro goes, oh, there's been an issue at the airport. Your plane's mechanical. Oh, we're so sorry. You have to stay here. I'll tell you what. Here's the best room in the hotel. I'll tell you what. Here's some more chips. Why don't you go play a little bit more? Enjoy yourself. The best room in the house on us. What happens? Loses everything he gained. Why?
You got suckered in.
Because of what Ryan just said. You can't beat the odds. The odds will catch you. He just got ahead. Remember, at the beginning of this simulation, that blue ball shot up to the top and then corrected down? What De Niro forced to happen was the Japanese businessman to force to be corrected down to 74. He popped up at 80 and then he stopped. He's like, I'm ahead, I'm done. If everybody gambled like that, Vegas would go bankrupt. But people don't gamble like that, do they? If I just play one more time, that machine looks hot. As soon as that old lady gets out of the scene, I'm gonna knock her over and take it. Keep thinking like that, and Vegas will continue to keep their lights on all the time and keep pumping Colorado River water in to pump the Bellagio fountain for you 24/7. Because you are paying for it. We are paying for it as gamblers because you can't fight the odds. And Vegas knows that, paratroopers know that, business people know that. All you can control is how much you pay or take on each of those odds. How much you pay for your premium, for your life insurance, or your car insurance, or your health insurance. Things like that. So that's what this course begins to kind of set the stage for, is understanding those kinds of quantifiers. Thank you, Ryan. It's a great analogy, fantastic analogy. And it's amazing how military paratroopers, Robert De Niro, and gambling and life insurance policies all operate on the same premise as this. It's amazing. Makes me wish that algebra wasn't called algebra. All right.